So one of you check once it starts. I started. Yeah, I think it is coming, correct?
Yes, it's working. Shantani and Harinder, we may start. Please be.
Yeah, Harinder, you can start.
Yeah, good evening all. I am Harinder Singh.
Hi, I'm Shantani, and I welcome you all to the day one of the talk on Introduction to Dynamical Systems by Professor Nikita Agarwal. This talk is organized by Curry Leaf, a math club of MTTS alumni.
Yeah. So we would now like to invite the President of MTTS Trust, Professor G. Santhanam, for welcoming speech. Professor Santhanam completed his PhD from TIFR, Mumbai, and is currently a faculty of IIT Kanpur. His research interest lies in differential geometry and has been associated with MTTS and as an integral part of MTTS. Now I would like to invite Professor Santhanam. Over to you, sir.
Thank you, Harinder. Good evening, everyone. It's a great pleasure. It's always very happy, glad to meet all the MTTS alumni, even if it is our virtual classroom. Yeah. And very glad that the relief activity for this academy has started. And I'm sure we will have many more talks, starting with one of our alumni, Dr. Nikita Agarwal. Dr. Nikita Agarwal, I think first time met her in 2005 in Pune MTTS. I very clearly remember that, she was saying that I want to go to America. So in fact, one of our picnic trip. You remember Nikita?
Yes.
Okay, marvelous. Somewhere we went. Okay. So what I want to say is that she was really focused at that time. And I'm very glad to see her back working in one of the very active area of research, dynamical systems. I do not take much time. I'm like you, I'm also waiting to hear from Dr. Nikita. So I wish all the success, and I'm sure all of you will enjoy this talk as much as I will do. Okay, Harinder, over to you.
Yes,
Yeah.
Thank you so much, sir, for your speech. So without further ado, let us commence with the talk. We are delighted to have amongst us today Professor Nikita Agarwal. Professor Agarwal completed her graduation from Lady Shri Ram College under Delhi University and went on to pursue MS and PhD in mathematics from University of Houston, Texas. She is also an MTTS alumni. She is currently an associate professor at IISER Bhopal.
Yeah. Now about her research interest, her main research interest lies in pure and applied dynamical systems. The topic included are dynamic of coupled cell systems, quantitative and qualitative study of attractor on smooth surfaces, application of dynamical systems and graph theory to the control theory problems, ergodic theory, and that is statistical properties of dynamical systems. Now, today she will be delivering a talk on introduction on dynamical system, and we would like to invite Professor Agarwal. Over to you, ma'am.
Thank you so much to the Curry Leaf team for inviting me to interact with this group. It's really a privilege and honor for me to come back to MTTS, this time on the other side. MTTS has been a crucial intervention in my academic journey. I think I'll put it this way. And it has played an instrumental role in where I am today. I'm glad that today we have a large group of MTTS alumni who are coming together and organizing such activities. 20 years back when I first time went to MTTS, there were only longer period MTTS sessions. Mini MTTS was not even there. Online was not even existent. So I'm so happy that today we have so many different mediums of getting training from fine mathematicians. And I also congratulate Curry Leaf team to for their efforts, for putting in so much of their time and energy and taking such keen interest in doing these activities. So let me now get to the topic of discussion for today. Dynamical systems is my area of research, and let me talk for a few minutes about how I got into this area. So I had never heard of dynamical systems, this term itself, before I went to Houston. At Houston, when I was doing a PhD or master's, there was a very active group of dynamical systems, people working in dynamical systems in various kinds of areas, ranging from information theory, from probability and statistics, from neuroscience, from ergodic theories, looking at statistical properties of systems, ordinary differential equations, so many different things. And all of them were sitting inside this big umbrella of what is known as dynamical systems. And because there were a lot of professors who were working in all these different areas, there were a lot of courses that were being offered. And incidentally, in my second semester of masters, actually the fourth semester of masters, I took a course in probability and statistics, in information theory, and a qualitative theory of ordinary differential equations. I'll touch upon few of these things in today's and tomorrow's session. But I was so excited to see how whatever I had learned so far was coming together. And it was really interesting for me, and that opened up my interest in this broad area of dynamical systems. And as Professor Santhanam said, it's a very active area of research, not just among mathematicians, but also amongst physicists, amongst engineers. So you will see people working in dynamical systems in several departments across any institute, working on different kinds of problems, but with a similar theme. And let me talk about what that theme is. So what is dynamical system? It gives you a framework. This dynamical systems theory gives you a framework to understand how complex dynamical systems behave. So let me break whatever I said in pieces and let me explain it to you what a dynamical system is. So let me share my screen first. I hope you can see my screen.
Yes.
Okay.
Yes.
Okay. So we are going to talk about So what is a dynamical system? It is a triple of three objects. The first is what is known as a state space. The second is what is known as a parameter space. And the third is a rule or a law. Let me come to these one by one. So what is a state space? State space is the space in which motion of a particle or some kind of dynamics of a system is happening. Okay? So I'll just say that space where motion takes place. Things will become more rigorous in a few minutes. Let me put these objects in really broad terms. What is a parameter space? What is a parameter? Parameter is parameter describes basically I should say the path. Okay. Again, I'll come to this in a minute. What is a rule? Rule is a rule that describes how the motion takes place. So this is kind of an informal definition of dynamical system. Now, coming to parameter space, there are broadly two categories. One is it could be the space of natural numbers or the space of integers. So this is classified as discrete, or you could have a subset of the real line, more specifically an interval, and this is classified as a continuous. So when your parameter space is one of these, you say that it's a discrete dynamical system, whereas if it's a subset of R, let's say an interval or all of R, you say it's a continuous dynamical system. Okay. So let me explain the concept using a few examples. So let us look at the first example where I focus on continuous dynamical systems. So continuous dynamical systems generally arise from solutions of ordinary differential equations. So I'm keeping the talk at really elementary level, in the sense that I'm not going to get into really advanced versions of all these definitions. I'm going to give you a head start into this area. So therefore, when I say that we are going to look at solutions of ordinary differential equations, don't think that that is the only way of coming up with continuous dynamical systems, but that is a more general, I would say that I'm going to stick to that notion, okay, where continuous dynamical systems are coming from solutions of ordinary differential equations. So let us consider this very simple ordinary differential equation, x dot equal to x, where x dot is the derivative of x with respect to t, and x belongs to the real line and t belongs to the real line. Okay. So this R is actually the phase space where the motion is happening. And again here the parameter space is also R, because the motion is described in terms of t, which is the parameter, right? So all of you know that given this ordinary differential equation and an initial condition, so take an initial condition, so assume that at time t equal to 0, you are at the point x naught in R. You know that the solution is given by, there is a unique solution, and solution is given by xt equal to x naught e to the, right? And this solution is defined for all time t in R, all t in R, right? So what is the rule? So we already have a phase space, we have a parameter space. What is the rule? Rule is this. This is the rule, which is telling us that if you start at the point x naught, then at time t, you're going to be at this point in the real line, right? So if I look at R2, which is where you want to draw the solution curves. So let's say this is the t-axis, this is x t. Then you start at 0, you start at some point x naught, and when you look at a curve, right, this is how it looks like. So this is x naught e to the t, right? And if I take x naught here, then you know how to draw the curve. So such solution curves are also known as flows. So why are they called flows? Because when you look at these solution curves, they are like flow lines in the space that you are looking at. So here, where am I drawing this picture? I'm drawing this picture in R cross R, which is parameter space cross the space, right? So I would like to write it as follows. So you take a map phi from R cross R to R as phi t comma x naught equal to x naught et. And this is precisely my rule. And how do I read it? I read it as follows, that if I start at t equal to 0 at the point x naught, then after time t, or at parameter, when parameter value is t, I am at this point in R. Okay, so this is my rule. So R, which is the phase space, R, which is the parameter space, along with this phi gives us a dynamical system. And it gives us a precise way of describing how the motion happens in the space. Okay, that's one way of looking at it. But if you look at the original equation, that also gives you a rule or a law of motion, right? Because this gives you an infinitesimal way of how the point moves in the space, right? That's what we learn in the calculus course, right? So this also gives a rule, right? And I am interested in this. Okay, I'm interested in, rather than solving a differential equation. So you have to keep in mind my words, because I'm going to come back to this concept in a while. I am not so interested in finding the precise solution, but what I'm interested in looking at what is known as qualitative behavior of the system rather than the precise solution. And you will see why it is important. So I'm going to look at this rule rather than this rule, which is easy to derive for this particular problem, but may not be easy to derive in general, right? If I give you a complicated differential equation, you may not be able to solve it. So the question is, do you stop there and you say, I can't solve it, therefore I cannot tell you anything about the motion? No. There are ways in which you can understand the motion by just analyzing the given differential equation. Okay, so we'll come to this concept in a while. So this is a way to come up with so I just gave you an example, but now you can formalize a general setting for a continuous OD. So let me give you the general setting. So general setting is the following. You take X in Rn and you consider the differential equation x dot equal to fx, where f is a function from Rn to Rn, and we place a few conditions on it just so that we know that there are solutions. So I'm going to place that condition to be f is not required, but I'm putting it to be continuously differentiable, because I'm going to talk about a very important result in differential equations that will emphasize this idea of qualitative behavior of solutions rather than coming up with a precise solution. Okay, so therefore I'm putting this, but you don't have to worry about it at the moment. So we have the system. So for given initial condition x naught in Rn, you can talk about solution of this system. Let me call it 1. Okay. So in this case, what is your phase space? Your phase space is Rn. That's a bad notation. Your phase space is Rn. Your parameter space is T, because I'm taking x dot equal to dx dt. So my parameter space is R. Again, I'll say a few things here at this point. This need not be all of R. Okay? So your solution may not exist for all time t. So we may have to restrict it. Again, we'll come to that in a minute. But it's a subset of R, right? So that's a parameter space. And what is the rule? Rule is either you think of this P T x naught as the rule or this equation itself, right? So that gives rise to a continuous dynamical system. So now let me come to example of discrete dynamical system. So let me first explain to you what is a discrete dynamical system. Just to motivate you, so suppose you start a walk from your house back to your house in the morning, and you record your coordinates every 1 minute. Okay, so every 1 minute you record where you are, at which location you are, right? What are your coordinates? That describes your motion at a discrete level, right? So after every 1 minute, you see where you are, you record that point. Again, 1 minute later, you record where you are, you note down that point. So you get a discrete set of points which describe your trajectory, right? So if I reduce this time duration of 1 minute by even further, then you get more and more points, right? You start to get more and more points on your path back home, right? So very similarly, I'm going to define a discrete dynamical system where the underlying parameter is a subset of natural numbers or natural numbers, okay? So what is, again, this dynamical system, you have a phase space that we will describe in a minute. Your parameter space is either natural numbers or all of integers. I'll explain how, and you will have a rule. Okay. So let X be a set. I'm not placing any mathematical constraints on this set at the moment. Your parameter space is N or Z, and you have a self map X. So by self map, I mean a map from X to itself. Again, I'm not placing any properties, any mathematical properties on this F. So what you do is you take a point X in X and you look at its orbit under F. So how do you define orbit under F? As follows. So you take X naught to be X, X1 to be F of X naught, which is F of X. You take X2 to be F of X1, which is F of X, right? We call it F square of X. X3 to be F of X2, basically the image of the previous point, which is F of F square of X, which is F cube of X. In general, you have Xn plus 1, which is F of Xn, which is F to the n of X. And so this is for all n greater than or equal to 0. Okay. So what you're doing is you're applying this map again and again on X, and you're seeing where the point is moving in X, right? Because F goes from X to X. All these points are in capital X space, right? And if F turns out to be invertible, by invertible I mean if it is 1, 1 and on 2, then you can also talk about the backward image, right? So then you can look at x negative 1 to be f inverse of x negative 2 to be f inverse of x negative 1, which is f inverse of f inverse of x, and so on. So I'm not spending too much time on this, but you understand what I'm saying. You can also go backwards in time, right? If f is invertible, but you see generally in dynamical systems, maps are not invertible. So we only talk about one-sided orbit. So let me give you a precise example of a discrete dynamical system. So consider x to be closed interval 0, 1, f on x to be defined as fx equal to x squared. So this is my rule or law governing the motion. Now what happens when you apply this map again and again to a point? So there are two points which are fixed for this map, right? So if I apply f on 0, I get back 0. If I apply 1, f on 1, I get back 1, right? That means if I look at the orbit of 0 or the orbit of 1, nothing happens. The point does not move at all. Okay. So these are called fixed points. Now the question is there any other fixed point? Very quickly, you can tell me that there isn't in this interval x, right? So now the question is, what is happening to other points? The orbit, right? So all of you know that if I take any number x in open interval 0, 1, and I apply f on that point, it goes to the left, right? X square is less than x. And then again I apply the map, I again go to the left, right? So in general, xn plus 1 by the rule I described above, fnx is x to the 2n, right? Is it 2n or 2 to the n? Let me ask this question. Is this or this? I don't know if audience have access to mic.
Yeah, they can unmute. Yeah.
Okay, that's fine. So I will leave that as an exercise. Okay, you see whether it should be this or this. It's not difficult to see. So one way in mathematics is to, all of us are used to this, giving competitive exams, and we can put in values and see which one works, right? For n equal to 2, it so happens that both are the same, right? So you really have to go to 3 to check. But in any case, it's not difficult. I'll leave it to that. But no matter which, in this case, what happens is if I take limit n goes to infinity, xn plus 1, that's 0, right? So no matter which x, where I start on open interval 0, 1, ultimately I'm going to 0, right? And that's all I care about. Why? Because when we all of us understand the concept of limit here, right? What happens? What is the definition of limit? When do you say that a sequence of points converge to 0? When no matter what cutoff you set, no matter how small interval you take around 0, there'll be a finite n value after which everything will be in that interval. All the points will be in that interval, right? Which means that very quickly, sorry.
Xn plus 1 equal f power n plus 1 x, maybe. You did.
Yes, that's right. Yes.
Yeah, thank you.
Yes, so thank you so much. So I'll just change it to, so let me, do this just to save some effort. So xn is fnx. Yeah. Thank you. So what I'm trying to say is that no matter how small interval you take around 0, in finitely many steps, you are going to land up in that interval. Of course, if you take a very small interval, then you will need a lot of iterations to come to that point within that interval. Or if your interval is big enough, then you can come to that interval in short span of time. But nevertheless, you are going to get close to 0, right? So in terms of dynamics, not much is happening here. Anything which is not 0 or 1 is going to 0. And this is the underlying feature. This is what we want to understand in dynamical systems theory. We don't want to get precise orbit, but we want to see how the orbit behaves eventually or asymptotically. Okay, that's the idea. So now let me give you another example of discrete system. So let us consider T going from x to x, where x is closed interval 0, 1, and this map is defined as 2x modulo 1. So this can be written as 2x when x lies between 0 and half excluded, because at half it becomes 1 mod 1, which is 0, and it is 2x minus 1 when your x lies between half and 1. Okay. So you can draw the graph of this function. So generally when maps are from interval to interval, we draw a box. Okay. And then at half, there is a shift. So you go like this. Right? This is how the graph of the function looks like. So if I want to understand what is happening to the orbit of any given point, I have to do more work than what I did for the previous example, right? Because it's not straightforward. The point is jumping from one side of half to other side of half. And how do we determine that, right? So it looks like a simple example, at least at this level where we stated it, but to understand its dynamics, so is called, is challenging. Okay. So I'm going to describe this map in a different fashion now, and you will see how various areas come together. So now you consider the same map, but now think of it as a map from circle, unit circle to unit circle. Okay, where I'm thinking of unit circle as collection of angles which describe where you are on the circle. I'm stopping at I'm not including 1 because if I include 1, then that point is same as 0 as far as the angles go, right? So what do I mean by this? So if I take the unit circle, this is 2 pi theta. Okay. So when theta equal to 0, you are here. This is theta equal to 1 by 4. This is theta equal to half. Theta equal to 3 by 4. And then back, I'm not including 1, but as theta approaches 1, you converge to this point from the bottom, right? Like this. So now you consider the map T of 2 pi theta equal to 4 pi theta. Okay. This can also be written as T of E 2 pi I theta equal to E 2 pi I 2 theta. So here I'm thinking of a point here on the circle. I'm thinking of this as sitting inside complex plane, the circle sitting inside complex plane, and I'm viewing this point as this, a complex number with modulus 1. Okay. So what is this map doing? So let us draw a nice picture now. So if you start with a point at angle 2 pi theta, it goes to 4 pi theta. So this point goes to this point, right? So what is happening now when you do this? The angle doubles, right? Now, when the angle doubles, if you were at 0, you stay at 0. If you are at 1 by 4, you go to 1 by 2. If you are at 1 by 2, you go back to 0, right? So half of the circle, when you apply the map, goes to the entire circle, right? But then there is this bottom part of the circle. What happens to that? It again wraps around the circle. So when you apply this map on the unit circle, the image is what? It is the unit circle, but the unit circle has now wrapped around itself twice. Right? And this map is called doubling. So doubling refers to doubling of the angle, and also that if you take any 2 points on the circle and you apply the map on both the points, the angle between them doubles, right? Of course, you have to be careful how far these points are and so on, but the angle in some sense doubles if the points are sufficiently close to each other. You can take it as an exercise and do many things with this example, but that is why it's called the doubling map. It's a very famous example in dynamical systems that one wants to learn. Okay. And these two maps are connected. How are they connected? Via a simple intervention, which is that instead of this X, you look at the quotient space where you identify 0 and 1. Okay. So if you identify 0 and 1, then what happens is once you hit the roof, which is value 1, you know that 1 and 0 are equal, so you come back to 0 and then you go on. So it is like wrapping around the circle twice. You can make it mathematically more precise, but these two are essentially the same maps, written differently. Okay. So is there any question so far? Okay. So while we are on discrete systems, let me give you another example. So another example is what is called as rotation. Okay. So again, you take S1 to be your state space. You take a map T on S1 as follows. So fix alpha in 0, 1, open 0, 1, and you define Tx to be, so I should be careful, T of 2 pi theta to be 2 pi theta plus alpha for all theta. So what are we doing here? We start with any point on the circle, 2 pi theta, and we move it, rotate this by angle theta, angle alpha, sorry. So this further angle is 2 pi alpha. We move this point here to this new point. This point. And this is what we do for all the points, right? So this map is what is known as isometric. Why? Because if I take any 2 points, theta 1 and theta 2, or rather 2 pi theta 1 and 2 pi theta 2, then the distance between them and the distance between their images on the circle is the same, right? Because I have moved both the points by the same angle alpha or 2 pi alpha, right? So as far as describing this map goes, it's very easy. But the question is, what about the dynamics? Okay. So let us understand the dynamics. So I'm going to take a particular value of alpha. So let us take alpha to be a rational number, p by q. Okay. So now if I start with a point 2 pi theta, in one iteration of the map T, it goes to 2 pi theta plus p by q, right? Then you apply T again, you get 2 pi theta plus 2p by q, right? And you can assume that p and q are co-prime. So what is going to happen is in q many steps, you are going to reach theta plus p, right? If I apply T q many times. But what is this point? This point is same as 2 pi theta, right? On the circle. So this means that the map, corresponding map for this alpha is what is known as periodic. Why? Because if I apply TQ many times to any point, it keeps it fixed. Right? So when alpha is a rational number, orbit of any point is nothing is happening in terms of dynamics. It goes around and it comes back to itself, right? Then again, if you apply enough number of times, it will come back to itself and so on. But the things become very interesting if alpha becomes an irrational number. I'm focusing on 0, 1. So note that when alpha is 0 or alpha is 1, it's the identity map, right? So therefore, I'm focusing on 0, 1 because that's kind of a branch which defines a unique class of maps, right? If I expand this range, then you get more and more maps, but they are same as this range, okay? So, so if I take an irrational number, then what happens? Then this is not happening, right? What I just described for a rational alpha. This will not happen because there's no multiple which is going to bring you back to the same point. So one thing is easy to prove, that there are no periodic orbits. Okay, you can show that if you start with a point and you move around, you let n go, take any value, it is never going to come back to itself. That's an easy exercise. But what is difficult is to show, not so difficult, but you can take it as an exercise, is to show that if I take orbit of any x in, I should not say x, any 2 pi theta, any 2 pi theta in S1, orbit of any 2 pi theta in S1 is dense. So I believe many of you are undergrads here and may not have yet learned the concept of dense. By dense, I mean that if I take any point on the circle and any interval or arc as small as you wish, there'll be a point of the orbit of this point which will land in this interval. Okay, I'll repeat. By dense here, I mean that on the circle, if I take any point, and no matter how small the interval around it, there will be a point in the orbit. So that means there is some n such that t to the n 2 pi theta will lie in this interval. Okay, that's what I mean by density here. So not just the points are going everywhere, not coming back to the original point, but they are going everywhere on the interval. And in fact, there are more properties that one can say, which is called equidistribution property, that they are not just dense, but they're dense in a very symmetric way, in a very nice way on the circle. Okay, that property is called equidistribution property. And there's a famous theorem that I think we will talk about it tomorrow. Okay. So the map at the definition level is very easy, right? But when you try to understand the map from dynamics point of view as to how orbits are behaving, that's when interesting things start to show up. And this is one of the properties that we have seen. Okay. So I'm going to talk about one more example. I'm giving you different kinds of examples, and why? Because I want to borrow some features of these examples later on. Okay? These are examples which are important. Like in mathematics, every example is important to understand the concept. These are examples which kind of give us understanding of various concepts that are there of interest in the theory of dynamical systems. Okay, so another example is something which is close to me because I work in this area of symbolic dynamics, and where symbolic spaces are of relevant. And those who have seen maybe a functional analysis course would have seen this example that I'm going to talk about. Okay. So what are symbolic spaces? Not in this form, but in some form. So what are symbolic spaces? So you take X to be I'm going to first write down what the space is. This is sigma to the n, which is the collection of all maps from n to a fixed set sigma 1, 2 up till k, where k is greater than or equal to 2, naturally. Okay. So this is how you denote the collection of all maps, but in essence, they are nothing but sequences. x1, x2, x3, dot, 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 such that xn belongs to sigma for all n belonging to. So you're looking at what are known as one-sided sequences with entries from this fixed set sigma. Okay. So when I looked at closed interval 0, 1, when I looked at unit circle, I did not care much about the properties of the space, because I kind of assumed that, you know, all of us understand the notion of distance there and what is the topological property of that space, right? I did not care about that at that point, but here I have to, because we have to put a structure on the space, right? So, so I'm going to talk about a few concepts from topology, metric spaces, but if you're not aware of it, if you've not taken a course there, you can skip this part. But what you do is, this is a finite set. You look at discrete topology on this set. And this is a product space, right? So you can put product topology on this space. So you can think of this as a topological space. And the product topology here actually comes from a metric. So it's also a metric topology. I'm not talking about what the metric topology is here, but the product topology on this space actually comes from a metric. So let us not talk about that here. But this space is not just a space of sequences, but it has structure. It has topological structure on it. Okay. So now you define a map sigma going from x to x as follows. So sigma of a sequence goes to a sequence which is x2, x3, x4, and so on. So in particular, if you take sigma of x, where x is this point, the nth entry of sigma x is xn plus 1. Right? So what is this map doing? This map is just deleting the first entry of the sequence, right? So it's shifting to the left. So this map is called shift map, and this is called shift space, or the full shift space, where full refers to taking all possible sequences. Okay. Okay. So now the question is that if I start with a point, which is a sequence now, and I keep on applying this map, what happens? With a little bit of thought, you can give an immediate answer that it just keeps on deleting the first entry, right? So if I have applied the map n times, then the first n entries are gone, right? So this map is clearly not invertible, right? Because if I take pre-image of any point or any sequence, it has K pre-images, right? Because that first entry that I had deleted can be anything from the set sigma, right? It can be anything from this set sigma. So it's actually what is known as a K to 1 map. So K points in the space go to one single point, right? So orbits are kind of easy here. So, so if I take a sequence x1, x2, x3, and so on, it goes to x2, x3, and so on, which goes to x3, x4, and so on, and you know what happens, right? So in terms of dynamics, this map is kind of very easy to see, right? And that's what makes it so important. And tomorrow I'm going to illustrate how this can be used to understand the doubling map that we just described. So remember the doubling map, which doubles the angle on the circle. There is a deep connection between, so let me write it down. There is a deep connection between the doubling map and sigma on X, where just two symbols. Okay, these are called symbols, which are entries of the sequence. And in general, there is a large class of dynamical systems that can be studied or analyzed using this kind of coding. Okay, so this is called symbolic coding. And this area of mathematics is known as, of dynamical systems, is known as symbolic dynamics, which has been my area of interest for last couple of years. Okay. So I have given you a couple of examples of discrete dynamical systems. So I have half an hour left, and I'm going to first emphasize 2 points about dynamical systems and then come back to ordinary differential equations. Okay. So the first point is that dynamical systems in some sense are deterministic, right? So in what sense are they deterministic? So dynamical systems are deterministic. So deterministic is in the sense that are described by a rule, by a specific rule, right? Which is either the map F or the solution which is coming from the solution of differential equation. So it's described by a specific rule. So in that sense, it's deterministic. You can trace, you can know the future if you know the present, right? By applying the map again and again. But at the same time, it can also be what is known as chaotic. So I'm not getting into the mathematical definition of chaos, but by chaotic, I will give you an informal definition. By chaotic, what I mean is that 2 points that are close to each other in the space can have very different eventual behavior. Okay. which means that, let's say, example of doubling map, 2 points which are close, in one iterate, their distance become doubles, right? So if this distance is d, then this becomes 2d. Then in the third iteration, it's going to become 3d and so on, right? So this d may be really small, but what happens is as you take more and more iterates, then these points may go very far. This is just an illustration of this, what I have written down. And this idea is known as sensitive dependence on initial conditions. Okay, and if you may have heard of this term called butterfly effect, which is due to Lorentz. So this is one of the features that one sees in systems which are of course deterministic because they are given by a specific rule. But when you look at them from dynamics point of view, they are chaotic because you can't predict where the trajectory will land if you perturb your initial condition a little bit. So I'm putting it differently now. Here I said that the 2 points which are close by can have very different eventual trajectory. But what I'm saying now is that if you start with an initial condition and you perturb it a little bit, you don't know where you will land. Okay. Now, if you take the map x square, right? So if you take the point 1 and you look at its orbit, it stays there, right? Whereas if you perturb a little bit, you go less than 1, then the trajectory goes to 0, right? So that is kind of what we are trying to say. Okay, that map is, by the way, not chaotic from this point of view, but it has this feature, right? So this is what I want to emphasize, that even though maps are deterministic, the system is deterministic, but it can also show what is known as a chaotic behavior. So the other property I want to emphasize is the following. This is one. Second is that so if you are given a state space, right? So the properties of this state space determine how the motion should be, right? So the properties of the state space, and of course the map gives you how the motion is going to happen in the space, right? So for example, if you're walking on a road and there are bumps, then your motion is going to be described by those bumps, right? It's going to vary with those bumps. Whereas if there were no bumps, then you will walk smoothly or you will drive smoothly, right? So properties of the space describe how the motion is going to be, but you can also go backwards. If you don't know properties of a space, but you know how motion is happening, then you can predict how the state space looks like, or at least some properties of it. Okay. So again, if you are driving at uniform speed and then suddenly you notice that, you know, your speed, there is a variation in your speed, then you know that there's something bad on the road, right? There's something on the road that caused that change in your speed, right? So in dynamical systems, one wants to understand the dynamics of a system given the properties of the space, but also look at the backward problem where you know the dynamics and you want to predict how your space looks like. Okay, so these are kind of things that one studies in dynamical systems. And now let me explain this idea of, when I said that you are we don't want necessarily the solution of a differential equation, but we want what is known as a qualitative behavior of the differential equation. So for that, I will look at an example. So by the way, this qualitative study of ordinary differential equations, it started with Poincaré in the end of 19th century. And let me look at this example. Okay. So consider this OD in one dimension. So dx dt is x dot is equal to x times x minus 1. Okay. It's again more complex than the original problem that we looked at, but still handleable. You can solve it explicitly by the method of partial fractions, right? But let us not do that. Okay, so let us, if all we care about is asymptotic or long-term behavior of trajectories, then we need not solve it. Why? For a very simple reason. So first note that if x is 0 or x is 1, then x dot is 0. Okay? So all of you know that these are known as critical points or equilibrium points. Which means that if I start with these initial conditions, then the solution is just the constant solution. The system does not move at all. But the point is, these are the only points of that feature where trajectories remains constant. Because if you take any point on the real line other than 0 and 1 as the initial condition, then you never stay at that point. Okay. So let me do a very easy first derivative test. So this, so what you do is you plot 0, you plot 1 on the real line, and you basically determine the sign of x dot. So when x is negative, then what is the sign of the derivative? When x is negative, this is negative, and this is negative, so the sign is positive, right? When x is between 0 and 1, then this is positive, but this is negative, so the sign is negative. Again, when x is bigger than 1, then the sign is positive, right? So what does the sign of x indicates? Sign of x indicates that as t increases, what happens to the change in x of t, right? So this can be written as x prime t, right? So this sign is telling us how xt or the position is changing as t changes. So this means that if you start with an initial condition which is strictly bigger than 1, because x dot is increasing, this xt is also increasing, which means what? Which means the following, that if you take limit t goes to infinity of xt, when x of 0 is strictly bigger than 1, this goes to infinity, right? Because it keeps on increasing forever. And what happens if t goes to minus infinity? Again, when x naught is greater than 1, it goes to, where should it go? It goes to 1. It cannot cross 1. Why? Because of the properties of the system, it is infinitely differentiable. And 1 is a fixed point, so you cannot cross it, right? Once you land at 1, you have to stay at 1 because it's a fixed point or a critical point or an equilibrium. when you are here in this domain, then also you can write limit t goes to plus infinity xt and limit t goes to minus infinity xt. Now here, when x naught is between 0 and 1, what happens is x dot is decreasing, right? X dot is negative. So that means xt is decreasing if you take a point here. Which means that, again, by the same idea that you can't cross 0 and 0 is a critical point, if t goes to infinity, then this goes to 0. And if t goes to minus infinity, then it goes to 1. Similarly, if you are in this region, when x naught is less than 0, then limit t goes to plus infinity xt is, it's increasing, so it goes to 0. And limit t goes to minus infinity xt is minus infinity. Now, what have I done? I did not find a solution, but just looking at the sign of the derivatives, which we learn in calculus course, right? We know first derivative test. We can see how the solution is behaving. No matter where you take the initial condition, now you know what is going to be the eventual behavior of that trajectory. I don't know the exact solution, but I know the behavior. No matter which point you take, strictly greater than 1, you know all the points have the same fate, right? As far as eventual fate is concerned, right? They're all going to, in positive time, go to infinity, and in negative time, go to 1. Okay, this is what I mean by qualitative study of ordinary differential equation. Rather than finding a precise solution, you just focus on how the trajectories would behave eventually. Okay, and why is it important? For a very simple reason, that you cannot solve most differential equations. Right? So when we take a first course in differential equations, all the equations that are presented to us are actually solvable, right? We can solve them by one or the other methods that we learn. But you can tweak them a little bit and you will fall into a space where you don't know what to do. None of the methods that you have learned work, right? So what do you do then? You can still understand what is happening to the motion by doing analysis like this. I've given you an example just to motivate you as to, why it's not always important to find explicit solutions. In this case, you could have found explicit solution, and you can, by the way, check that this is what happens. But without a solution also you can do these things. So let me stop today's lecture by discussing a famous theorem in this area of qualitative study of differential equations, which is known as Hartman-Grobman theorem. So Hartman-Grobman theorem is due to two mathematicians, Philip Hartman and David Grobman, and they came up with the proof independently around 1960s. Looking at different variations of this, I'm going to present the most basic version of Hartman-Grobman theorem, but there are several generalizations that are available in the literature. So for undergrads, there may be things that I talk about which you have not heard, but you will understand the basic principles still. Okay. So let O be an open subset of Rn, where I'm taking n to be bigger than or equal to 1. So undergrads can think of it as an open interval in the real line if n is 1, or an open unit disk in R2 when n is 2, and so on. So you can think of in very simplest form as possible as an open interval or an open disk or an open ball and so on. Okay. And also assume that the origin belongs to O. Okay. So it's something that contains the origin. That's just for simplicity. So let F goes from O to Rn be a continuously differentiable function on O. Popularly, we say that F belongs to C1O. So it's differentiable and it's also the derivative is continuous. And F of the origin is the origin. So origin goes to the origin. Again, a technical assumption. You can, just for simplicity. Okay. So let P T be the flow or solution of the system x dot equal to f of x. Remember x, this is dx dt, right? So when you look at this system, remember x, we are thinking of it in Rn. So x is actually x1, x2, so on up till xn. And f is from Rn to Rn, so it's a vector valued function. So f also is like f1, f2 dot dot fn. So this system is actually, why do we call it a system? Because it is a system having n differential equations, right? That is why a system. Okay. So now let A be equal to the Jacobian of f at 0. So Jacobian of f at 0. So what is this Jacobian? This Jacobian is basically the following. So let me digress a bit. So if f is f1 to fn, then and x is x1 to xn, these are the coordinates, then df0 is a matrix, which is n by n matrix, and the ijth entry is del fi del xj evaluated at x equal to 0. So if you are aware of Taylor series expansion, and let us, for undergrads again, let us think of n equal to 1. So you don't have so many components, you just have one f, right? What is the Taylor series expansion? Your first term will be f0, about 0. First term will be 0, because f of 0 is 0. Second term will be f prime 0 times x, right? And that f prime 0 is basically this, denoted as df0 when you are in higher dimensions. Okay? So this is the Jacobian of f at 0. So a very important hypothesis is that assume that A has no eigenvalues with real part 0. Okay. So what do you mean by this? That So what do you mean by real part 0? Real part 0 means that the eigenvalues are purely imaginary. Right? Is there any question? Okay. So there are no eigenvalues which are purely imaginary. Okay. So all eigenvalues are such that there is a real part, right? Either positive or negative. No condition on that. So such a matrix is known as a hyperbolic matrix, which is a very important term in dynamics. Okay. So then something interesting happens. Then there exists a homeomorphism H from U to V, where U and V are open sets in Rn containing the origin, such that for all x0 in U, there exists an interval I x0 in R containing 0, such that for which if you take H of P T x0, that's equal to EAT H of x0 for all T belonging to x0. So what is it telling us? So when you look at the linearized system, which is given by x0 equal to df0x, so this is A. So why is it called linearized system? Because when you look at this fx, and let us think of the Taylor series expansion, the first term f of 0 is gone because f of 0 is 0. The second term is the linear term, right? Which is precisely this term, df0 equal to x. So this linearized system is actually the local behavior of this system f of x equal to f of x. So you ignore all the nonlinear terms and you just focus on the linear term, and this is called a linearized system. And the theory of ODE tells you that this has a solution which is given by xt equal to EAT x0. So this is called matrix exponential. Again, I think there was a lecture series by Professor Amar Habib who talked about linear groups. So I'm sure this matrix exponential was talked about there. This is the same matrix exponential, and this is the solution of the linear system. So if you think of this, then what is this? This right-hand side here is nothing but the flow of the linearized system starting at the point h of x0, right? Whereas on the left, what is this phi t x0? It is the solution of the original system, x dot equal to fx, starting at the initial condition x naught. That means this homeomorphism H gives you a way of going from the solution of nonlinear system, which is this original system, nonlinear system, to this linear system, right? This H gives you a way of going from the nonlinear system to the linear system solutions, right? provided that the matrix A is hyperbolic, right? So if I give you a nonlinear system, which is like x dot equal to fx, and you know that 0 is an equilibrium, meaning f of 0 is 0, and you also know that Jacobian has these features that it is hyperbolic, that none of its eigenvalues have real part 0, then what happens is locally, whatever happens in the linear system can be translated to the nonlinear system. So once you understand what is happening in a linear system, you can completely know the dynamics locally around the equilibria in the nonlinear system. Okay, so this is a powerful theorem in ordinary differential equations, which relates the linear system to nonlinear system in a specific setting of hyperbolic systems. Okay, and typically all systems are hyperbolic, right? Why? Because if, let's say, there is a system which has an eigenvalue whose real part is 0, and you perturb a little bit, you can come up with a hyperbolic system, right? So most systems, in mathematical sense, most systems that you see are actually falling in this category where you can apply Hartman-Goldman theorem, right? Because given a system, if the Jacobian at the equilibria is hyperbolic, then you know how the dynamics will be. Okay, so I will stop here. Tomorrow I'm going to begin with this theorem itself, and I will give you an illustration of this theorem, and then I'll talk about some other concepts. So I'll stop here.
Thank you very much.
Yeah. So thank you. Yeah. Over to Shantini.
Thank you so much, ma'am, for your talk. Participants in the Zoom meeting, if you have any questions, you can raise your hands and we will moderate that. Participants in the on YouTube, you can post your questions in the chat box. We will communicate the question to the speaker.
There is one question on YouTube, right?
Yeah, there is one question on YouTube regarding the doubling map. It said for theta equals to 0 and theta equals to half, how are the angles doubled?
So when theta equal to 0, it's a fixed point, right? So you don't move at all. So at that point, you don't double the angle, because that's if you look at the orbit and you apply the map, you stay there, right? At half, what happens is when you double the angle, half goes to 1, which is same as 0, right? As far as on the circle the angle goes. So half goes to 0 and then it stays there. So the orbit of half is what is known as eventually fixed, right? It's an eventual fixed point, because from half you go to 0, which is 1, and then you stay there. Same thing actually happens for 1/4, right? 1/4 would go to 1/2, and then 1/2 would go to 1, which is same as 0, right? So if I take any point of the type 1/2 to the power n, or in general, so let me open my my writing pad again, because it's a very interesting question. At least the question leads to something very interesting. I hope my screen is visible. So if I take any point of the type p/2 to the k in theta to be this, right? Any theta to be this. Then after, if I do 2 to the k theta, that is p, but at the circle level, this is an integer, so this is same as 0, right? So any point of this type, actually after repeated application of the doubling map goes to 0 and then it stays there. These points are very important. They are known as dyadic points. And you will see them in the next lecture. So thank you for asking this question.
Thank you so much, ma'am. Do we have any question on the meeting? You guys can raise your hands. Okay, there is another question from YouTube. Is there any proof of the map that you said is dense in case of irrational numbers?
So the question is that the rotation map, when alpha is irrational, why is the orbit dense?
The question is, yeah, is there any proof of the map that you said is dense in case of irrational numbers?
So I believe, I mean, I'll have to rephrase the question. I think the question may be that for irrational rotation, so when you rotate by an irrational number, I said that orbit of any point is dense. Yes, there is a proof, and it requires basic tools from real analysis. So if you have taken a course in real analysis, you can attempt proving that orbit of any point is dense. So to give you a head start, don't take any point, just start at the point 0. So prove that the orbit of 0. What is orbit of 0? When you add angle alpha, 0 goes to alpha, alpha goes to 2 alpha, 3 alpha, 4 alpha, and so on. Prove that on the circle, the points 2 pi n alpha, 2 pi n alpha, of course, modulo 1, they are dense on the unit circle. So just prove it for the point 0. So tomorrow I can start with this issue, and I can give you precise starting point for proving that orbit is dense.
Thank you, ma'am. We have one question from Soumya, sir. So you can go ahead.
Yeah, so do we have a similar map as tripling map? Like
Yes, we have actually, you can take, instead of 2x mod 1, you can take mx mod 1 for any m that is a natural number. Of course, m is 1, it's just the identity map. But then the feature is similar. If you, let's say, take tripling map, which is 3x mod 1, then it goes on the circle. It wraps around the circle thrice, right? These are important maps in geometry also, where we talk about degree of a map. Okay, from dynamics point of view, when I drew the graph of this function 2x mod 1, I had 2 slant lines, then you have 3 slant lines, and so on. And they are also interesting from symbolic dynamics point of view. So yes, there is a whole range of examples, not just 2x mod 1, but in general mx mod 1, which are known as expanding maps.
Thank you, ma'am.
Okay, ma'am, regarding the proof that you said about the dense case, the answer, it is asked that where they can find a proof, and if you can provide any reference for the proof.
Okay, so I think I will, before giving you a reference, I want you to think about it. So let me not give a reference today, because it's, as I said, it's an exercise worth trying. So let me again share my screen, and let me post the problem right away. Okay, it will take only 2 minutes, because then you can spend your evening in thinking about this. So I would like you to prove the following question. Okay, So remember the map was Tx or T theta equal to theta plus alpha, right? Where alpha I am saying is in 0, 1 intersection the irrational number. So it's an irrational number. What is the orbit of 0? 0 goes to alpha, alpha goes to 2 alpha, goes to 3 alpha, and so on, right? So prove that if I take n alpha mod 1, n greater than or equal to 0, what is this? This is the orbit of this point. This is dense in 0. Yeah, in 0. You can put closed interval because it doesn't matter. So just prove that this is dense in 0, 1. So I'm hesitant to give a reference today because I would like you to try this out yourself. Or if you are comfortable with computers, you can maybe try there. Just see what is happening to these points. You can plot them on the unit circle to see how these points are moving around. Okay. So remember to n alpha mod 1 is basically the angle is 2 pi n alpha. This is the angle. Yeah.
Thank you so much, ma'am.
Ma'am, I have a question.
Yes.
Ma'am, if you look at the doubling map, that is x goes to 2x, instead of taking x goes to 2x, if we take the map x goes to some 2 plus epsilon of x mod 1, is there the behavior of the doubling map and the new map same dynamically?
No, actually, because so it depends on what your epsilon is. Okay, so let's say if epsilon is again a rational number, then things are controlled in some sense, because again what you can do is you can come up with some kind of periodic structure. Okay? But if you have epsilon, let's say, to be irrational, then you can imagine that there is more complexity, right? Because the angles are not just doubling, but there is this irrational factor which gives you more complicated dynamics, as what happens here in this example of irrational rotation. So 2 plus alpha is not so straightforward. It's not similar to 2x mod 1. There is more that is happening there. But you can try maybe, for example, 2.01, if you can see something is happening, or you can try 2 plus epsilon, where epsilon is an irrational number, and see what is happening. So these are very interesting exercises. They can keep you occupied for several hours, and I'm sure you will notice some interesting features.
Thank you.
Okay. Is there any other question on Zoom? If you can raise your hand. Yeah, any question? So, Sianthini, is there any question on YouTube?
No, there are no more questions on YouTube.
So we can end this meet, but before that, we want to take in a group photo. Okay. So
There is another question.
yeah, let's take that question first. You can unmute.
Where can I refer to if I want to refer something? Any book to refer?
Sorry, you have to be louder. I didn't hear you.
Can you suggest a book to refer, ma'am?
Yes, I will do that today. So today I don't want to do that because I know that all of you will really jump there and to find several solutions to, a few small questions that came up. So I will do that today. That's my promise. And if you can't attend the session today, you can definitely look up the YouTube. But for benefit of everybody, I don't want to give references today.
Okay, there's a question on YouTube. How can we relate doubling map with Baker transformation map?
Okay, so there is an indirect way of relating the two maps, which is through what I defined when I talked about the symbolic spaces, right? Where we looked at the shift map. So there is a connection that way, not directly, but so tomorrow I will give some insight into that. But the point is both the maps, Baker's transformation and doubling map, they are studied using symbolic spaces, and one can attempt to find a connection between the two symbolic spaces to which they are related. Okay, so so I'll talk about it tomorrow, but I will also give references tomorrow, where you can find answers to this.
Yeah, thanks, ma'am. So is there any other question? I think we can wait for 1 minute. In that time, I request everyone to if they can open their camera. So we will take in a group photo. Yeah.
Yeah, slowly people are opening up videos. Yeah.
Somesh sir, are you taking a screen share?
Sure, I'll take. I'm waiting for the 4 remaining participants to open. Maybe. Okay, yeah, let's take them. Yeah. Oh, somehow it's not working. Harinder, go ahead. You have to take.
Yeah, I took one. Is everyone ready? Yeah, I took a couple. Harinder, you can take a couple if you want.
Yeah, I taken one. Okay. So let me go.
Yeah, I have taken 2.
Okay.
Thank you.
That's enough then.
Thank you, ma'am, for the very nice talk.
Thank you.
So we meet tomorrow at 4. Okay.
Okay. Okay, everyone.
You can